Okay, let's talk about how can I transfer energy from a system or to a system. Okay, as we discussed in thermodynamics, all I care about is the system. The thing that I don't really care about is called the surroundings, right? So, and as long as I have an energy transfer, maybe I can use it. Okay, so it's kind of important. But what is the forms? What is the forms that can take? What is the ways that it can take? That's what I want to investigate in this particular segment. Okay, but this actually will be separated into two. This will be one way for open systems. There will be another way for closed systems. Okay, remember that this open system is called to control volume. Closed system is called to control mass. So there's no mass transfer. Okay. So if in the most general sense, the open system is gonna have the ways is it can have a heat transfer, it can have a work, and it can transfer energy through mass. This and this seems obvious to you, okay? But the last one may not seem obvious. But if you think about this, I gave the example in module 1. I had a faucet turn on into a particular sink. There was some sort of a water inside of my sink, and there was a drain, right? So when I turn the faucet on at the very hot water, what will happen is the energy of that incoming water is going to change the energy of the system, which I will pick as the water in the sink. So this has the capability to add or remove energy from the system. So this is kind of important, okay? And the equivalent of these three methods that we have over here, well, obviously, just because a system doesn't have any mass transfer or closed system or control mass, heat transfer will still be there, work still will be there. Obviously, mass is gonna be gone. Okay, so that is like this is three ways. This is two ways to do it. Okay, in this particular segment, we will focus on or set of segments rather. We'll focus on the heat transfer. We'll focus on the work, and then we are gonna throw in some definitions for you to use. And down the road, there will be an entire module focused on the applying first law to the open systems, and over here I will explain mass in much more detail because I don't feel like explaining right now and then hang on for like several modules and then I go and revisit, right? So that's the game plan that I have. Just want everybody to be on the same page. Okay, let's start with the first one, which is the heat. So that will be common in both heat transfer. Okay, heat transfer is both for closed and open systems. But this is very important. I usually don't write, but this time I feel like writing it. This is the energy transfer due to temperature difference between the system, which I care about, and the surroundings. Okay, so when I talk about this, is I want to highlight right off the bat is this. Okay, I'll revisit that the next one, but energy transfer due to temperature difference. That is the only way something will be quantified heat transfer. Okay, the temperature of the system can increase without having any heat transfer. Let me repeat: the temperature of the system can increase or decrease without a heat transfer. Just because the temperature has changed, do not assume that there's a heat transfer that took place. Okay, so let me do this. I have a cup of coffee, right? It's 80 degrees C, and the surrounding is 25 degrees C. So see what's happening, or we can say 195 Fahrenheit. I have this over here as I don't know 50 Fahrenheit. I know it's not the same value, but that's fine. Right, there will be some kind of heat transfer, and what will happen is over time, if you think about this 80 degrees C is going to lower to 60 degrees C, then to 40 degrees C, then all the way to 25, where it will stop the heat transfer process. Okay, so it's kind of important. You can see that the heat is being transferred from here to here. Okay, this is the heat is leaving the system. Okay, so that is something that I would like to know. I'll give another example. Okay, just want to highlight what I'm gonna say next is wrong, but I'm gonna pretend it's right for a second, and then like, oh wow, wait. Okay, so I don't know you, but I have an air fryer and I love that thing. Okay, and this air fryer, just to highlight how it works, is this. I have a fairly strong fan. It is similar to the room fan, except it's much smaller. Okay, and I put my food over here. Okay, and whatever, the food gets warmer over time. Why? Because I have an inductive or resistive heating going on. Okay, so obviously as the temperature of my food goes up, the system is going through a heat transfer to heat my food. It would be wrong. Okay, why? Because it really depends on the system. The system is my air fryer, right? If my system is air fryer, my food is not getting hot because I have a hot reservoir or hot kind of like an environment over here, and this, we extract that heat and put it into the food. No, that's not how it works. How it works is this: there's an electrical energy that is coming into the system, resistive heating, right? It heats it up, and this fan pushes it to the food, so for more even and faster cooking. So basically, the goal here is to have this electrical energy is the initial form of it, and typically that is what it is. Electric energy has the highest quality that we know of. Okay, and then I just get the temperature of the food going up. So there is absolutely no heat transfer. Okay, let me correct myself. There may be heat transfer from, as the oven is getting hotter and hotter, there may be heat transfer from the system to the surroundings, but the way to heat the food is not through the heat transfer. Am I being clear? I'm not sure, but that's what I want to highlight over here. So like I said at the beginning, I don't want you to assume that just because the temperature of something is going up, it is automatically heat transfer. Okay, and I said that if no heat transfer, well, let's get a name for it. Like if no heat transfer between the system and the surrounding, I'm going to call this an adiabatic system. I use this terminology very often. Why? Because it's going to make your life easier. Okay. Now you see, let's go back. If I look at the open systems, I have 3 ways. If I look at the closed systems, 2 ways. If it's adiabatic, then I don't have to worry about heat transfer. Doesn't mean I should ignore the work component of it, which is next, that I'm going to talk about. But this is something that I would like you to be cognizant of. Okay, heat transfer adiabatic systems are easier to analyze because I don't have to deal with half of the energy transfer methods for a closed system. Okay. Now I in the previous segment I did this. I had a lowercase e will be equal to capital letter E divided by the mass, right? I'll do a similar to things for the heat transfer. So when I have basically over here heat transfer per unit mass, I will call this specific heat. Okay, specific heat. And if you look at the units, you can see this is joule per kilogram or BTU by pound mass. Okay, and I call this specific heat. Okay, important. We use this often as well. Okay, very similarly, we have a Q dot. Okay, Q dot, heat transfer rate. Heat transfer rate. I want to highlight in the previous segment, I said that when I have a capital E, I call a capital E dot. I call that a power. Okay, I was doing kind of on purpose because I was assuming the system was adiabatic. So this is called power as long as the system is adiabatic. I don't call this a power. Just want to highlight. Sometimes I see this kind of feedback like heat transfer rate. This is called heat transfer. This is not power. Okay, that's not the official terminology for it. Okay, and most of the time in the heat transfer rate, I really want to go from the heat transfer rate to the heat transfer because that's what I care about, right? As you will see in the first law. So as this is heat transfer rate, which means that it is per unit time, okay, per unit time. But that I don't want to write here like here is equal to Q divided by T because that assumes Q is constant. Q may not be constant throughout my process. And for instance, looking in here, for instance, my coffee, right? My coffee 80, 60. Do you think the heat transfer rate will be the same at 80 to 25 to, I don't know, 60 to 25? Right? So that reason I'm not going to write that. But what I would like to write now is I'm going to say that this heat transfer rate is variable. So then the way to obtain the Q will be this. Integral from time 1 to time 2 between 2 times Qt dt. You see? It's the same thing. I'm multiplying Q by T. Let's not forget the dot. Very, very important. My bad. Okay. Heat transfer rate by time. I'm doing exactly what I said, but I do a little bit more on the fancier side, okay? And there may be a case where heat transfer rate is constant. So then what I will do is well, if this is not a function of time, I can take constants out of the integral. So you can think this is like 5, 10, 20, 1 million, doesn't matter. It's just a number. So I can take this out of the integral. So then, okay, fine. I get myself q dot t, and then I will get myself t1 to t2 dt, right? And the integral of that will be q dot t and t evaluated at t1, t2. So you can see in here, I'll get my q as, q dot times delta t, where you can see from the integral is t2 minus t1, right? So this is this. So this is kind of important. We use this as well. Next, I want to talk about the work. Actually, once I covered the heat transfer, the work is fairly easy, because if, I'm going to write it here, if energy crossing the boundary of my system to the surrounding is not it, then it's work. Fairly, so you can think of this, work is like everything else. Okay, so I have heat transfer, perhaps, or not. The rest of it all is called the work. So it's kind of not that, hard. Okay, and I have the same things as what I did up there. I'll start by this. Q divided by m is called the lowercase q, right? Same thing over here. So lowercase w will be capital W divided by mass, but you can also use this as, like units wise, joule per kilogram. By the way, I keep saying joules, right? But joules is so small. Typically we use kilojoules, but the SI is, B2 per pound mass. Okay, so these are the units of it. I can do the same thing for here, heat transfer rate. Now this is called the power. Okay, W dot, that's called the power in terms of the watts, in terms of the units. This is joule per second, or I can have BTU per hour. Okay, don't ask me why we are using per hour. I kind of know the reason, but I'm gonna explain down the road. Okay, so same thing as up over here. So I can have this W will be T1 to T2. Power, the work, is equal to power times dt. Okay, and if this is constant, just like what I did, I can do this W dot, which is a power, is constant power is applied, then I'm going to have delta T, where delta T will be basically T2 minus T1, right? You see, I'm using a sign now. This is watts, this is joules. Do not confuse the units, please. Okay,